Okay, what's up, guys? This is attempt number two. First time I recorded this, I found out that I forgot to turn on my microphone, so I did the whole thing, and I have to redo the whole thing, but it's okay. So, this is electric field lines and conductor properties. So you can see a picture here of two positive charges, and what you see are the red electric field lines that are coming off of those charges. So you remember that positive charges have electric fields that are pointing away from them. So we're going to look at why this diagram looks so much more complicated than what we saw before. Don't worry, it'll make sense, I promise. Okay, so just a brief review. You remember that electric field lines come from when we compile all the force vectors that are on a test charge that are placed around an existing charge. So you remember that we started with this central charge here, this black one that you can see in the middle there, and we started placing a bunch of little positive red test charges around that charge. And the red arrows represent the direction of the electric field and the strength of the electric field at those points. And so we kind of started getting a picture of what the electric field was at each of those spots based on putting a positive test charge there if we had a central negative charge. So what you can do then is add up all of those different ones by figuring out what would the electric field look like at each of those different points, and you kind of get a map of, generally speaking, where's the electric field pointing at different spots. And that's what you do in order to picture what the electric field looks like, and you end up making what's called a vector field. And the electric field, or the electric force, is a vector, so the electric field is just a field of vectors. So if we go further, we can connect all of the dots of all those little points, and we make field lines. So we get this nice, consistent view of all the electric field lines all connected to each other. So all of the directional information is compiled to give us these really cool looking field lines. So we get two kinds of information out of this. You get both the direction and the strength of the electric field at all locations around the charge. So we're going to first look at the direction, and then we'll look at the strength after that. Okay, so the direction of the field lines is all about the positive test charge. And we talked a little bit about this before, and you see the example on the right that if the electric field is pointing towards the upper right direction, if we were to put a positive charge there, then we see, oh yeah, the electric field goes in the same direction that the electric force would on that charge. And if we put a negative charge, then the electric force goes in the opposite direction. So remember, the electric field lines always point in the direction that the force on a positive test charge would point. So that's why you can see the positive charge has the force and the electric field are parallel, and for the negative charge, the force and the electric field are what we call anti-parallel. They're pointing in the opposite direction from each other. So positive charges are always what we use as the test. Now, the vector lengths of the electric field and the electric force are different because the electric field is, remember, defined as the electric force divided by the charge. Or in other words, the force is equal to the charge times the electric field. So we could say, oops, we could say F is equal to Q times E. This is kind of like the gravitational force, if you remember when we said F equals mg, right? So the gravitational field, that's G, is pulling upon masses to give them a gravitational force. Well, in the same way, we have an electric field E that is pulling or pushing on electric charges, that's Q, to give them an electric force, that's F. So the different size masses changed how strong the force was. Well, just like with that, when we have different size charges that are in the same field, you get a different force. So as we learned before, on the left side, you can see that for positive charges, the electric field lines always point away, and for a negative charge, the electric field lines always point towards. And again, that's because what would a positive charge do? If you have a positive charge next to another positive charge, it wants to get pushed away, so the lines point away. If you have a positive charge next to a negative charge, it wants to get pulled in, so the lines point in. Now, what if you have a positive and negative charge that are next to each other like this? Then you end up with this really interesting looking diagram. This is what we call an electric dipole. Di meaning two, and pole meaning, well, yeah. So we have a positive and negative that are next to each other. And if you kind of look at this central line right in the middle between the two, I'm going to try and draw it right here. Right down the middle there. That central line represents every spot that is exactly in between the positive and negative charges. Now, what's really special about that is the electric field uh, at that point. If you were to draw the electric field from the positive charge at that spot, it would look like this. If you were to draw the electric field from the negative charge at that spot, it would look like this. Now, the horizontal components are both going to add together to point that way, but the vertical components of these things, one's going up, one's going down, they're going to cancel each other out, so you get only the horizontal part. So that's why at every spot in that central line, all the electric fields are pointing straight to the right. So it's a really special kind of thing. And you can see the electric field just kind of loops around in this really neat way, that it all leaves away from the positive charge and loops around and goes towards the negative charge. And that's what electric dipoles do. They have these really cool kind of loopy features. And you can see that the electric field is always tangent to the field lines at every point. So you can see this one right here, that at this spot, if you were to put a test charge right there, the electric field points immediately perpendicular from that test charge, from the point where that test charge is. And so the field lines kind of follow and track where the charges would move perpendicularly. So if we look at now the strength of the field lines, so last slide we looked at the direction, but the field lines also show us how strong the field is. So if we look at the density of the lines, we find that the greater the number of field lines that are entering or leaving a point charge illustrates the magnitude of the charge. And also, the number or density of field lines at any point is directly proportional to the field strength and the magnitude of the charge. So that means if I look at A, B, and C, you could easily say that the order of strength of charge on each one is increasing from A to C. A has the weakest charge, B has the medium charge, and C has the really big charge because there's a higher density of lines around them. Not only that, but the closer that the lines are to each other tells you how strong the field is at that point as well. So if I were to take a little charge and put it right here, which is closer to charge A, you can see that the distance between the field lines is close together. So that means the charge, the field that the charge feels at that spot is really strong, which makes sense as we were looking at earlier. Remember the formula is F equals K Q1 Q2 over R squared. So just like with gravity, the closer the objects are to each other, the smaller the R, and since R is on the bottom, that makes the force get really big if R is really small. So if the charge is really close, then it has a really strong field. Whereas if I were to take a test charge and put it way out here, now you can see the field lines are really far away from each other. They're spaced out. That means that the charge or the electric field at that point is actually much weaker. So as the lines spread out, the field gets weaker. And you never actually change the number of lines that you have. You always keep the same number. So you wouldn't like start at this random point here and say, well, I'm going to add a new line and create a new field line that starts over here just to keep them spaced. No, you wouldn't do that. You start with whatever number you have and watch them spread out. And that's what allows you to maintain that the integrity of that field density. So we learn two things from watching these fields. We see the direction and we see the strength of the field at every point based on where the arrows are pointing and based on how spread out or closely packed they are at that spot. And now we want to take a look at field lines due to multiple point charges. This gets a little bit tricky, but earlier we saw an example of an electric dipole. Remember, the field leaves from the positive charge and goes towards the negative charge. So the field lines will always, when you're interacting with two types of charges, they will either always connect or they will try to veer away from each other. So in this case, if you have a positive and a negative, they try to connect because you will imagine a charge will try to go from the positive towards the negative. And of course, the directional and magnitude rules that we have from before still apply. Now, if you have two positive charges, this is where you can see the field lines try to veer away from each other. And this is because if you imagine a positive test charge, you were to put a little positive charge right here in the middle between the two, right there, it wouldn't want to go towards either one. The right side is trying to push it away and the left side is trying to push it away. So where does it go? Since it's right here, they're both going to have an upward directional force on it, so it's going to get launched upwards. And any other place, it's just going to get pushed by both of those charges. So all of these lines try to push away from each other because any charge that you put is going to try to run away from those charges, which makes sense. Now, if you have an interesting case like this, where you have an imbalance of charges, say on the left you have a single negative charge, and on the right you have a double positive charge. You can see it looks pretty similar to the same case that we had on the upper left, except this time, because the positive charges are stronger, it's actually going to push even harder away than the positive charge that we saw before. So you can see that it's similar shape, but the shape is kind of warped in favor of the stronger charge. So that if you look more closely at the stronger charge, it looks more like the star shape that we saw from just a single charge on its own, because it kind of dominates the shape of the field. And depending on, the different kinds of arrangements, you kind of just follow those principles and imagine how strong it would be. Or you could actually do the math and you could calculate how strong is the field from one object or the other. Like if I chose this point right here, I could say that the field from the right charge is going to be pointing this way. And then if I have the negative charge, I see that the field is going to be pointing this way. And you can see that one is stronger than the other. So because of that, the field is going to have more of an upward leftward direction at that spot than it is a downward leftward direction. So you can see the slope of the field at this spot is actually aimed slightly upwards, which makes sense because the charge on the right has more influence than the charge on the left. That's why it has this warped kind of shape. So for practice, I want you guys to try this yourselves, wherever you are, if you're at home or if you're watching in class or whatever it may be. Why don't you give it a try and see if you can draw the field lines for two interacting negative charges that have the same magnitude of charge. And I will give you a hint that it's probably going to look very similar to what it looked like in the last slide when we had two positive charges with the same magnitude. Except if you remember what a single positive charge looked like versus a single negative charge, they have the same shape, just the field lines are pointing in the opposite direction. So I wonder if you might see something similar for having two negative charges compared to two positive charges. Another one I want you to try is to do field lines for two interacting charges where one has a charge for Q and the other has a charge minus Q. And another hint, this is probably going to look really similar to that last example that we saw of one negative Q and two positive Q on the other side, except it's going to be even more intense. And it's going to be even stronger bias towards the 2Q, this time 4Q, positive side. So probably similar shape, just more extreme in the imbalance that we saw. So why don't you give that a try? Hence, you might see something like this on a possible future quiz or test. So it's good to practice this kind of thing.